let's say I've got some linear transformation T that is a mapping from Rn to Rn. So if this is its domain, which is just Rn, that is Rn, and then its codomain is also Rn, If you give me some vector in our domain, let's call that vector x, then T will map it to some other member of Rn, which is also the codomain. So it'll map it over here. And we could call that the mapping of T, or the mapping of x, or T of x. And since T is a linear transformation, we know that the mapping of x to its codomain is equivalent to x being multiplied by some matrix A. So we know that this thing right here is equal to some matrix A times x. You've seen all of this multiple times. And just to make sure we understand the wording properly, we've used the word that A is we could either call it the matrix for T, or let's say it's the transformation matrix. The transformation matrix for T. Now, in the last couple of videos, we've learned that the same vector can be represented in different ways. It can be represented in different coordinate systems. And when I just write the vector x like that, we just assume that it's being represented in standard coordinates, or it's being represented with respect to the standard basis. So let's be a little bit more particular. A is the transformation for T only when x is represented in standard coordinates, or only when x is written in coordinates with respect to the standard basis. So let me write a little qualifier here. A is the transformation for T. A is the transformation matrix for T with respect to the standard basis. With respect to the standard basis. I never wrote this blue part before. I never even said this blue part before, because the only coordinate system we were dealing with was the standard coordinate system, or the coordinates with respect to the standard basis. But now we know that there are multiple coordinate systems. There are multiple ways to represent this vector. There are multiple ways to represent that vector, because Rn has multiple spanning bases, or there's multiple bases that can represent Rn, and each of those bases can generate a coordinate system where you can represent any vector in Rn by some with coordinates with respect to any of those bases. So that last part I said was a bit of a mouthful, so let me make it a little bit more concrete. Let's say that I have some basis B that's made up of n, it has to be linearly independent, that's the definition of a basis, of n vectors, v1, v2, all the way to vn. Now, these are n linearly independent vectors. Each of these are members of Rn. So B is a basis for Rn, which is just another way of saying that all of these vectors are linearly independent, and any vector in Rn can be represented as a linear combination of these guys, which is another way of saying that any vector in Rn can be represented with coordinates with respect to this basis right there. So the same vector x, the same dot here, when we represent it in standard coordinates, we write, it's just going to be that right there, that vector x. But what if we want to represent it in coordinates with respect to this new basis? Well, then we could call that same vector x will look like this. Or we would denote it by this. The same vector can be represented with respect to this basis. So this could be some set of coordinates. This would be some other set of coordinates, but it's still representing the same basis. Likewise, this vector right here, that vector right there, is also in Rn. So it can be represented by some linear combination of these guys. Or you can represent it with coordinates with respect to this basis. So that same point right there, I could represent it. So that point is this. But I could represent it with coordinates with respect to my basis, just like that. So this is an interesting question. This should maybe bring an interesting question into your brain. If I start off with something that's in standard coordinates, and I apply the transformation t, that's like applying this matrix A to it, or multiplying that thing in standard coordinates times the matrix A, I then get the mapping of t in standard coordinates. Now, what if I start off with that thing in non-standard coordinates? If I have coordinates with respect to this other basis here, well, t should still map it to this guy, right? The transformation, no matter what, should always map from that dot to that dot. It shouldn't care what your coordinates are. So t should still map. So let me draw another. T should still map to that same exact point. T should still be a linear transformation, and it could map from x to t of x, but that's the same thing as mapping from this kind of way of labeling x to this way of labeling x. So we could say maybe t could be this maybe this guy right here could be some other matrix times this guy over here. So let me write this over here. So maybe t, I mean, these are just different coordinate systems. So maybe I shouldn't just even say maybe. This guy should be able to be represented. So if I represent the mapping of x in our codomain in coordinates with respect to b, so that's what that guy is right there. So if I want to represent that dot with this other coordinate system, with coordinates with respect to this basis, I want to represent it. It should be equal to the product of some other matrix. Let me call that other matrix D. Some other matrix D times this representation of x times the coordinates of x with respect to my alternate non-standard coordinate system. I should be able to find some matrix D that does this. And then we would call D, we would say that D is the transformation matrix for T, and A was with respect. A assumes that you have x in standard coordinates, but now D assumes that you have x in this other in coordinates with respect to this basis. So with respect to the basis B. No reason why we shouldn't be able to do this. These things are just different ways of representing the exact same vector, the exact same dot in our sets here. So if I represent it one way, the standard way, I multiply it by a, and I get ax. If I represent it in non-standard coordinates, I should be able to multiply it by some other matrix and get another non-standard coordinate representation of what it gets mapped to. So let's see if we can find some relation between D and between A. So we learned a couple of videos ago that there's a change of basis matrix that we can generate from this basis. And it's pretty easy to generate. The change of basis matrix is just a matrix whose columns are these basis vectors. So V1, V2, no, I shouldn't put a comma there. These are just the columns. V2 all the way to Vn. This is an n by n matrix. Each of these guys are members of Rn, and we have n of them. This is an n by n matrix, and where all of the columns are linearly independent. So we know that C is invertible. So these are all column vectors right here. So we know that C is invertible. And we learned in the last 2 or 3 videos that if we have some vector x, if we have our vector x, and it's being represented by coordinates with respect to our basis B, we can just multiply that by C. We can multiply that by C, and we'll get our vector x. This is essentially, it will tell us the linear combination of these guys that'll get us x. And since C is invertible, we also saw that if we have just the standard format for x, or the standard coordinates for x, we can multiply that by C inverse, and then that'll get us the coordinates for x, with respect to B, with respect to the basis B. And these two things, if you just multiply both sides of this equation, let me do a different color. If you just multiply both sides of this equation by C inverse on the left-hand side, you're going to get this equation right there. Now, given that, let's see if we can find some type of relation. Now, we know, or we're saying, let's see what d times xb is equal to. So let's say if we take d times xb, so this thing right here should be equal to d times the representation or the coordinates of x with respect to the basis b. That's what we're claiming. We're saying that this guy is equal to d times the representation of x with respect to the coordinates with respect to the basis b, right? So let me write all of this down. Let's scroll down. I'll do it right here because I think it's nice to have this graphic up here. So we can say that d times xb is equal to this thing right here. It's the same thing as the transformation of x represented in coordinates with respect to b, or in these non-standard coordinates. So it's equal to the transformation of x represented in this coordinate system, represented in coordinates with respect to b. We see that right there. But what is the transformation of x? What is the transformation of x? Well, that's the same thing as a times x. Right? That's kind of the standard transformation. If x was represented in standard coordinates. So this is equal to x in standard coordinates times the matrix A, and then that will get us to this dot in standard coordinates, but then we want to convert it to this non-standard coordinates. Just like that. Now, if we have this, how can we just figure out what the vector ax should look like? What this vector should look like? Well, we can look at this equation right here. We have this. This is the same thing as this. And so if we apply, or actually no, we want to go the other way. We have this. We have that right there. That's this right there. And we want to get just this dot represented in regular standard coordinates. So what do? We multiply it by c. So let me write it this way. If we multiply both sides of this equation times c, what do we get? We get this right here. Actually, no, I was looking at the right equation the first time. We have this right here, which is the same. First intuition is always right. We have this, which is the same thing as this right here. So this can be rewritten. This thing can be rewritten as C inverse. We don't have an x here. We have an ax here. So C inverse times ax. Right? The vector ax represented in this non-standard coordinates is the same thing as multiplying the inverse of our change of basis matrix times the vector ax. This will essentially, if I have my vector ax and I multiply it times the inverse of the change of basis matrix, I will then have a representation of the vector ax in my non-standard basis. Now, what is the vector x equal to? What is the vector x equal to? Well, the vector x is equal to our change of basis matrix times x represented in these non-standard coordinates. So this is going to be equal to C inverse A times x. X is just the same thing as C. X is just C times our non-standard coordinates for x, just like that. So what is let me summarize it just because I waffled a little bit on this point right there just because I got a little bit confused. If I start off with the non-standard representation of x, or x in coordinates with respect to b, I multiply them times d. So if I start with this, I multiply them times d, I get to that point right there. So this right there is the same thing as this point right there. That point right there should be the non-standard representation of the transformation of x, the non-standard representation, or the coordinates of the transformation of x with respect to b. Now, the transformation of x, if x is in standard coordinates, is just a times x. So this is just a times x, but I want to represent it in these non-standard coordinates. Now, a times x in non-standard coordinates, is the same thing as c inverse times a times x. Right? If you think this is the same thing as this. And so if you have this and you want to represent in non-standard coordinates, you multiply it by c inverse. So then you'll get that representation in non-standard coordinates. And then finally we say, look, x is the same thing as c times the non-standard coordinate representation of x. So x we can replace x with that right there. And so the big takeaway here is that d times the coordinates of x with respect to the basis b is equal to c inverse a times c times the coordinates of x times the coordinates of x with respect to the basis b. And just like that, we have a version. So d must be equal to c inverse ac. So if d is the transformation matrix for t with respect to the basis b, and let me write here, and c is the change of basis matrix for b, then, and we know A is the, let me write that down, and, might as well, because this is our big takeaway, and A is the transformation, I'll write in shorthand, transformation matrix for t with respect to the standard basis, then we can say, and this is the big takeaway, that D, our matrix D, is equal to C inverse times A times C. That's our big takeaway from this video, which is really interesting. I don't want you to lose this point. We now understand that A is just for a certain set of coordinates, but there's an arbitrary different bases that we can use to represent Rn, so we can have different matrices that represent the linear transformation under different coordinate systems. And if we want to figure out those different matrices for different coordinate systems, we can essentially just construct the change of basis matrix for the coordinate system we care about, and then generate our new transformation matrix with respect to the new basis by just applying this result.